Okay, let's check if this works. So thank you for the introduction. My name is Kristjan Vuk Baliž, and I'm a teaching assistant here at the faculty. I also work as a researcher. So my topic is actually how to use the, for instance, silicon on insulator microring resonator for a particular application for improving a millimeter wave radio over fiber transmitter. So basically, from the telecommunications point of view, we would like to transmit as much data per unit time as possible, and to achieve this, we have to have a good transmitter, and the transmission path as well plays an important role in this, and a receiver as well. So I will actually now focus on the problem that arises from the physics that happens in the transmission path. So in particular, we're talking here about the optical fibers, the single mode optical fibers. So what happens there is that we mostly, when talking to single mode optical fiber, we mostly talk about the dispersion phenomenon. So in particular, the chromatic dispersion, which basically limits the bandwidth of the transmission. So the problem is that by using a conventional transmitter consisting of a laser source and Mach-Zehnder modulator, we produce such a double sideband spectrum. And because of the dispersion in the fiber, one of the sidebands gets shifted in phase differently than the other sideband. So what might happen at the end of the transmission path, so at the receiver side, is that both sidebands are out of phase for certain lengths and or modulation frequencies carried by this transmission path. As I said, this is dependent on the length of the transmission path, so the optical fiber and or the modulation frequency, and this figure here actually shows what happens. So the blue lines here, the blue areas correspond to combination of length and modulation frequency that do not allow any power to be transferred. So there are actually these dips. If you look along one or the other axis, we have these dips in power, which is also described by the equation there. Obviously we want to mitigate that, and the traditional approach to doing this is just to use the special kind of fiber, so dispersion compensating fiber, or dispersion compensating module, which can be tuned for the particular configuration of the transmission path, so the link. And by doing that, we basically compensate the dispersion. But let's look now at some more modern approaches. So this was basically a research that we conducted using the dispersion module, the tunable dispersion compensation module, and we just wanted to show that by using this device we can effectively compensate the power penalty, which means that instead of these dips we get like a smooth curve there, the green one. But there's a problem with the traditional approach. So the problem basically is that if we have, let's say, point to multi-point network topology, we encounter the problem that we have to basically install the compensation mechanism in every receiver, so which is complex and expensive and does not allow for any configuration changes in this network once this is set up with the compensation modules there. So the more modern approach would be to use, let's say, a microring resonator. So use the transfer function of such a resonator to get rid of one of the sidebands in the double sideband profile of our signal. So we did that with the help of photonic integrated circuit that was provided by Professor Wim Bogaerts from the Ghent University. So we investigated many ring resonators on that chip and tried to identify the appropriate one or the suitable one for the job. So obviously what we found out is that we want to have a high extinction ratio in the through direction of this microring resonator in order to be able to suppress one of the sidebands as much as possible. And another condition, another requirement is the FSR, so the free spectrum range. It is favorable for it to be greater than the wavelength difference between the sidebands. So that only one resonance gets into the area of interest. So that we don't have any problems with other resonances. So the results from using these micro-ring resonators enabled us to more or less get rid of the dispersion penalty, which happens. So this is the graph that shows the behavior in the length-dependent function, and this is for the frequency-dependent function. Okay, so this was the setup. Just to show the scale of the setup. So the setup was like was configured on 4 meters long table, but the main element, the responsible element for treating this problem is like 3 centimeters by 1 centimeters in dimensions. So so that was the ring resonator that we used on that chip. Yeah, but the problem with ring resonators is that they're highly susceptible to temperature fluctuations. And what happens is that the resonances shift with time, which is obviously unfavorable because we want to suppress the undesired sideband by a constant amount. So we don't want that to be dependent on time, right? So yeah, so this figure actually shows what happens. So we were able to treat the behavior by suppressing one of the sidebands, but due to the temperature sensitivity, then this gets corrupted once again. So the next task was to treat this problem. So we continued with our research activities in that direction. So the idea then was to use part of this signal. So the signal that gets, the sideband that gets suppressed in the through direction, so the direction towards the receiver, we can capture that energy in the drop port. And in the drop port, we get the reciprocal situation. So we get the most energy when the most energy is suppressed in the through direction from that sideband. So the idea is to use that energy as a feedback information, as a feedback signal to drive or to provide the feedback information to our control loop system in order to lock the wavelength of the laser to the wavelength of the microring resonator. So we choose that approach. This approach is a little bit different from other approaches. So most of them treat that by using the integrated heaters on the photonic circuit. But we decided to keep the things simple, so to use the simplest possible microring resonator, so without any integrated heaters and so on, and to take the advantage of the conventional DFB laser that most of them have the heat pump installed already. So we wanted to use that to align the carrier wavelength to the resonance of of the microring. So we had to study the process a bit, so all the components in order to be able to configure and to design the control loop system. And so one of the drawbacks of this approach is obviously the time constant that characterizes the system. So the system between the heat pump and the laser. So how the changing current or voltage that controls the heat pump affects the laser wavelength. So indeed, this approach is quite slow, but nevertheless, we got it to work. So the microring resonator used here was one that allowed us to have as much energy as possible coupled to the drop port when in resonance. So this was kind of a requirement to get a signal that is strong enough for the feedback signal. So this was the control loop system block schematic that we came up with. So the idea was basically to get the signal from the photodiode, to take the derivative of that, to mix it with a reference sawtooth signal, and to use an integrator to basically find the correct value. So to align the wavelength such that maximum energy is coupled into the photodiode at the drop port. So this is the electrical schematic of the control circuit, and this was the setup that we used to assess the results of our approach. So we managed to stabilize the temperature to the extent that only 4 picometers of jitter remain. So this was the capture from the oscilloscope. It is not that important for this presentation, I suppose. And this was another setup by help of which we kind of determined how successful we were in stabilizing the system in terms of the power penalty. So this basically shows the power deterioration at the receiving end because of the chromatic dispersion and the power penalty for different misalignments, of the laser source. So we managed to somehow stabilize the laser and to keep it below 4 picometers from the optimal wavelength, which basically allowed us to keep the power penalty below 2 decibels. So the power penalty deterioration, so how much the power penalty gets worse because of the fluctuation that still remains in the system. Okay, so that was the setup accommodating this experiment, and I would like to thank at this point to Professor Janez Krč and to my colleague András de Belc, who were also involved in this research. So with that, I would like to conclude the talk.
Thank you. Time for questions. Kristjan, I guess you have also some ideas for further experiments. Can you, in few words, say about that?
Yeah, well, one of the ideas obviously is to get this system a little bit better. And beyond that, we are looking into a possibility to design and to manufacture a specific microring resonator, a special microring resonator that would allow for even better results. So we're looking into some coherent application that would allow us for better detection of that feedback signal and so on. Yeah.
Okay. Yes.
So you put a microring after the EDFA, which means you put quite some power in the silicon chip. Did you see any, and silicon is also quite nonlinear in terms of response. Did you see any effects of that, or were the coupling losses in this chip too high, or the Q factor too low?
Yeah, well, let me just show that figure here. The problem was, in order for this for us to perform the experiment, we had to use, let's say, non-optimal configuration of the Mach-Zehnder intermodulator. So we didn't really have it biased at the quadrature point, so the -3D point, but we configured it for a different carrier to sideband ratio in order to be able to have the sidebands at the drop port expressed enough to have a relevant feedback signal. So that basically means that we unfortunately had to attenuate the signal by non-ideal configuration of the Mach-Zehnder modulator, and then we brought that back by the EDFA. So, I mean, other than that, we didn't really pay too much attention to the nonlinear effects.
So the power before the chip is Z? You cannot. So it's C.
Yeah, so it's right there. Yeah.
Yeah, but I can't read the value.
So it's 9.6.
Okay. Yeah. So on the chip it's 5 dB or something. So it's.
Yeah.
Okay. Okay. Yeah.